In lecture 10b of differential equations in linear algebra, I want to start by reviewing lecture 9b, reviewing part of it, at least cross products and equations of planes. I decided I would like to do an example of how to find the equation of a given plane going through 3 non-collinear points. Then the bulk of what we do in lecture 10b will be looking at a 5×2 linear system arising from something called the least squares problem. And we'll think about the associated linear transformation, what's its image, what's its kernel, that kind of thing. When you talk about images and kernels, it's more than just academic. It really is helpful later on in thinking about lots of different things. So please pay attention to it. So let's go ahead and jump in this PowerPoint to the linear algebra content. Starting right here, cross products in 3 space. I'm going to go over this very fast because I want to get to that example. So given 2 3-dimensional vectors, like I mentioned in 9b, they have to be 3-dimensional vectors. V and W, their cross product is another 3-dimensional vector. Dot products are numbers, cross products are vectors. That actually causes some people to call the dot product a scalar product and the cross product a vector product, even though we're always dealing with vectors. So it gets a bit confusing, but that is the case. Here's the crazy looking equation. Got 3 components. The first one, you're looking at cross products, so to speak, with the minus sign of the second and third components, V2 times W3 minus V3 times W2, which is what you see there. The third one is a similar thing with the first and second components, V1 times W2 minus V2 times W1. The middle one, the second one, is the same, except you must put an extra minus sign in there. We're looking at the second row there, so we focus on the right here, so we focus on the first and third rows here. V1 times W3 minus V3 times W1, then put a minus sign in front of it, but of course you can then also distribute the minus sign through the parentheses. We talked about properties of dot products. These are something you should know. There's also something called the right-hand rule, which I briefly mentioned in lecture 9b. I'll talk about it more today here in this lecture in the context of an example. And the example is going to be to try to find the equation of a plane when we are given 3 distinct non-collinear points, not on the same straight line. You you create new vectors, V and W, that are not the same as the V and W up there, by subtracting coordinates of points appropriately. And now the labels they don't matter as long as you're consistent. And you see 2s and 1s here and 3s and 1s there. You could also switch them around, 1s and 2s and 1s and 3s, as long as you're consistent. You could also do 3s and 2s and 3s and 1s, that kind of thing, when you look at these differences. As long as you stay consistent with the subscripts that you see. You let n be V cross W, and it turns out the equation of the plane is given by this dot product equaling 0, that is a dot product there. And you should be able to simplify that to a scalar equation that looks like this. So let's do an example. Let's be given 3 points. I'll call them P, Q, and R. In rectangular coordinates, I'm just making up numbers here. 1, 0, -3, 0, 2, 5, and -1, 2, 1. Let's say those are our 3 given points. Are these non-collinear? I made them basically randomly, so they're almost guaranteed to be non-collinear. I would almost bet lots and lots of money on it, but I'm not a betting person. So, for example, we could let V be the vector whose components are the second point's coordinates minus the first point's coordinates. So 0 minus 1, there minus there, 2 minus 0, and 5 minus -3. That'll be -1, 2, 8. Let W be similar kind of thing, except we'll use the third point as well, its coordinates. -1 minus 1, 2 minus 0, and 1 minus -3. Simplifies to -2, 2, 4. And the cross product of V and W turns out will be normal to the plane of V and W, orthogonal to it. That's going to be the property that we need to guarantee that this gives us the right equation, because because the dot product is going to be 0. The dot product of two orthogonal vectors is 0. And this is a general vector of the plane. I'm using subscripts of 1 there, but I could use 2s or 3s consistently. All right, so I'm focused on these two things and the corresponding cross products. So I'd have, careful here, 2 times 4 minus, I have to be careful here. Now I should have these things next to each other. 2, 2, 4. 2 times 4 minus 8 times 2. Negative, in parentheses, negative 1 times 4 minus 8 times negative 2. And then finally, in the third component, negative 1 times 2 minus 2 times negative 2. I will check this in Mathematica to see if we got the right answer here. So this is 8 minus 16 is negative 8. Inside here we have negative 4 plus 16 is positive 12, but the minus sign makes it negative 12. And here we have negative 2 minus negative 4 is negative 2 plus 4 is 2. So it looks like that's a normal vector. The cross product, let's double check that with Mathematica. I'll show you how to do that here. V is going to be actually let's do it with the points first. In Mathematica, when you use curvy braces like this, it can either be thought of as a point or a vector, and it can be worked with either way. P has coordinates 1, 0, negative 3. Semicolon suppresses output. So it's sort of what I use to separate different lines of code. Q has coordinates 0, 2, 5. And R has coordinates negative 1, 2, 1. Just make sure I didn't type those wrong. 1, 0, negative 3, 0, 2, 5, negative 1, 2, 1. Okay, I can enter those. And then I can type V equals Q minus P, treating Q and P as if they were vectors instead of points. Mathematica doesn't care. Negative 1, 2, 8. That matches right here. Does the other one match that one? Negative 2, 2, 4. Do R minus W equals R minus P. Negative 2, 2, 4. And then to do the cross product of those two things, I type cross in square brackets V comma W. That does V cross W. Negative 8, negative 12, 2. Yes, correct. And I'll also show you, we could have done it the other way around. We could have done W cross V, and like I mentioned last time, that's the opposite of V cross W. You have the same thing. These two things are the same except for minus sign. Negative 8 becomes 8, negative 12 becomes 12, 2 becomes negative 2. Actually, you can use either one as a normal vector. So now let's see. Here we go. That's what I can use for n. Then I can dot it with an arbitrary vector in the plane, which I can write in this way, where x, y, and z are going to be variables. So we're going to take negative 8, negative 12, 2, and dot it with x minus, I'm going to use the first point, minus 1, y minus 0, and z minus negative 3. Set that equal to 0 and continue simplifying. So we have negative 8 times x minus 1. I'm doing a dot product now. Minus 12 times y plus 2 times z plus 3 equals 0. And I don't know if I'm out of room here or not. This is going to simplify to negative 8x minus 12y plus 2z equals something on the right-hand side. It'll be the constant term added to both sides. Negative 8 times negative 1 is positive 8. 2 times 3 is 6. 8 plus 6 is 14. So I'd subtract 14 from both sides. That's an equation of the plane containing these 3 points. I also could multiply both sides by -1 and get 8x plus 12y minus 2z equals positive 14. And that would be what I'd get with the other normal vector that comes from the cross product of w cross v. Okay? And hopefully I haven't made a mistake. I'll try to correct it when I process the video if so. All right, for the rest of the time, oops, wrong thing there. For the rest of the time, let's look at our least squares application and the corresponding linear transformation that's related to it. The linear transformation that I think about that's related to the system is not something well, it will come into play in one way. I shouldn't say it's not something you don't need. Initially, I was dealing with linear transformation just to illustrate the idea of the kernel in the image, but it'll still be good to think about. We will be able to interpret it correctly. So what's a least squares problem? It arises when, for example, you want to fit data points to a straight line. So I've got 5 data points, and I'm trying to fit a straight line to those points. Now, those 5 points do not all lie on a line exactly. I'm trying to find the trend of the line. And to solve for the line, really what I need to do is I need to solve for the unknown slope and intercept. Let's call the unknown line f of x equals mx plus b. This is going back to pre-calc, calc 1, etc. This is a linear function. For that kind of class, it's not a linear transformation. I really want to find m and b to make the graph of this function fit the data as well as possible. So I need to plug in the x-coordinates and set them equal to the corresponding y-coordinates. So I'm going to get 4, looking at this first point here, x is 1, y is 4, I get 4 equals m times 1 plus b. For the second point, I plug in y equals 3 and x equals 2, I get 3 equals m times 2 plus b. For the third point, x is 3, y is 3, I get 3 equals m times 3 plus b. For the fourth one, I get 2 equals m times 4 plus b. And finally, for the last one, I get 0 equals m times 5 plus b. Try to solve that system of 5 linear equations and 2 unknowns for m and b. And it should make intuitive sense that it's probably not possible. You have more equations than unknowns, most likely there's going to be no solution. So are we stuck? Is there truly no solution? Well, let's go to the Mathematica again. This time I pre-type stuff. Here's the data. Here's the plot of the data. Remember, those points are not in a straight line, but I can fit the trend. Try to find a line looking approximately like this that fits the data as well as possible. Intercept's going to be somewhere around 5 or 6 something. Slope, maybe a lot, or close to -1. And in fact, this Mathematica command fit will actually find that line. It's got an intercept of 5.1 and a slope of -0.9. So it looks about like that. M is -0.9 and B is 5.1. But wait a minute, I thought I just said a minute ago that there should be no solution. There is no solution to the system exactly. There's no exact solution to the system. It's overdetermined, inconsistent. However, it does have a least squares solution. You might call it an approximate solution. What's the best we can do? Before we get into what that answer is, though, let's think about the corresponding linear transformation. This defines, again, a system of 5 equations and 2 unknowns, a linear system. We can write it as one vector equation and separate out the left-hand side into a linear combination of 2 fixed vectors. Notice 1, 2, 3, 4, 5, and 1, 1, 1, 1, 1 are the coefficients of m and b. And this vector has components equal to the right-hand side numbers, 4, 3, 3, 2, 0. As we've talked about recently in recent lectures, this could be thought of in terms of a matrix times a vector equals some other vector. In fact, a 5 by 2 matrix times a 2 by 1 vector must give you a 5 by 1 vector. This is 5 by 2, 5 rows and 2 columns. This is 2 by 1. The fact that the 2's match, the inner 2's, means you can do the multiplication. And the answer is going to have dimensions equal to the outer numbers. It's going to be 5 by 1, thought of as a matrix. Why did these correspond to each other? It was the definition of matrix times a vector. A matrix times a vector is a linear, when you can actually do it, is a linear combination of the columns of the matrix with the coefficients or the components of the vector as the weights. So we get m times the first column plus b times the second column, which is what you see over here. And this can be thought of as a matrix, call it capital A, and a vector, call it boldface x, and another vector, a constant vector, call it maybe boldface c. That's what it did there. And this defines a linear transformation from R2 to R5, because the input is 2-dimensional and the output is 5-dimensional. T, going from a 2-dimensional space mapping into a 5-dimensional space. Can you visualize such a thing? Only by analogy, not literally. At least I'm not capable of it. Should make some intuitive sense because of the dimensions that there's no way this function can be onto. But maybe it could be 1-to-1. That's what I say here. Such a transformation cannot be onto. No way. If you're going linear transformation from a lower dimensional space to a higher dimensional space, there's no way it can sort of expand the dimensions to make the function onto. In fact, it doesn't even hit the particular vector c. It doesn't even hit. By hit, I mean there's no x such that t of x equals c. There's no solution of this equation for x. We'll find an approximate solution, but not an exact solution. But how do you confirm for sure that it's not onto? That this particular c is not hit? You have to do row operations on an augmented matrix like we've been talking about recently as well. So this is a 5 by 3 matrix where the first 2 columns are the same as the matrix capital A, same as the coefficients of the left-hand side of these equations in the system, and the rightmost column, the third column, is the right-hand side of the system of equations. It's the right-hand side vector, it's C. Again, I like putting a dashed line in here to separate off the coefficient matrix, so to speak, from the right-hand side one. You don't have to, okay? We want to do row operations to try to get this into reduced row echelon form, which basically means every row has either a leading 1 or it's all zeros. Another thing in reduced row echelon form is for any given row, the leading 1, the first one that you see, should be to the right of the first one in all the rows above it, if there are rows above it. There should also be zeros below any leading 1 and all zeros above any leading 1. And the 3 operations that are allowed are row swapping, back and forth. That's like swapping equations. It doesn't change the solutions of the system. Multiplying any row by a non-zero number, equivalent to multiplying any one of these equations by a non-zero number to get an equivalent system. And the most important one, the row replacement operation. Multiply any given row by a certain number and add it to the other row. Put the answer in the other row. That's row replacement. That's also valid. That's analogous to multiplying one of these equations by a number, including even 0 in that case, and adding it to another one, maybe to cancel the m's, to eliminate them. And that's the idea here. This 1 is a leading 1 in this row. So the first step of the algorithm is to make all these zeros below it by doing row replacement operations. Multiply row 1 by -2 and add it to row 2. Put the answer in row 2 to make this one a 0. Becomes -2 plus 2 is 0. Multiply row 1 by -3, excuse me. Add it to row 3 to make that one a 0. Multiply 1 by -4 to get a -4 there. Add it to this row to get a 0 there. And multiply row 1 by -5. Add it to the third row to get a 0 there. So we'll get zeros below the leading 1 from the first row. What's going to happen to the other numbers? These other numbers are going to change too. The first row, though, is going to stay the same. It stays fixed. So for example, what's this number going to change to? I'm multiplying row 1 by -2 and adding it to row 2. 1 times -2 is -2, plus 1 is -1. This is going to become a -1. What about that number right there? 4 times -2 is -8. -8 plus 3 is -5. This is going to become a -5, etc. The ones I just talked about. What about the other ones? For example, what about this one right here? That's in row 4. I multiplied row 1 by -4 and added it to row 4. So 4 times -4 is -16, plus 2 is -14. That's what you see right there. Take the time to double check these. So I got one leading one still here in the first row. I don't see any leading ones in any of the other rows. Let's move on to the second row. That's not a leading one, it's a leading -1. But if I multiply this row by -1, that's an allowed row operation. I'll get 0, +1, +5. And that'll be my next leading one in the second row. And I want to get zeros below it. I did those two things in two steps here. So I imagine this becoming a 1 and a 5. Then I imagine multiplying row 2 by 2 and adding it to row 3 and putting the answer in row 3 to make this a 0. 2 times 1 is 2, plus -2 is 0. 2 times 5 is 10, plus -9 is 1. What about third row here? After I have a 1 and a 5 there, I multiply row 2 by 3, add it to row 4, and put the answer in row 4, making this -3 become a 0. 4 times -3 is -12. Excuse me, sorry, looking at the wrong thing. 5 times 3 is 15, plus -14 is 1. Finally, for the fifth row, I multiply the second row by +4 when I have a 1 and 5 there to make this a 0 here. And 5 times 4 is 20. 20 plus -20 is 0. So now I've got leading ones here, here, and here. I also want zeros below them and zeros above them. Turns out you work from right to left now. You start with this leading one and put zeros below it and zeros above it by row replacement operations. Because you got zeros in these spots, the other numbers in the other columns are not going to be affected. So I got a 0 right here by multiplying row 3 by -1 and adding it to row 4 and putting the answer in row 4. These were not affected because you get 0 plus 0. To get 0 here, I multiply row 3 by -5 and add it to row 2 and put the answer in row 2 to get a 0 right there. These two spots were unaffected because of the zeros here and here. And to get a 0 there, I multiply row 3 by -4, add it to row 1, put the answer in row 1 to get a 0 here. This one was not affected because 0 plus 1 is still 1. Even -4 times 0 is 0, and plus 1 is still 1. One final step is to put a 0 above this leading one, multiply row 2 by -1 and add it to row 1, put the answer in row 1. We'll make that a 0. This will stay a 0, this will stay a 1. Here's the reduced row echelon form of this 5 by 3 augmented matrix. In terms of a system of equations, an equivalent system to the original system, this is saying m equals 0, b equals 0, it's a b there, and what's this one say? It says 0 equals 1, 0m plus 0b equals 1, and that's a contradiction. We got a contradiction, that can't happen. So what does that mean? It means there's no solution. Remember that the logic of solving equations says start with the system and assume there's a solution and find out what it could be. But if you get a logical contradiction like 0 equals 1, that means your original assumption that there was a solution must be wrong, and there is no solution. All right, I'm going to go faster. Any more row operations, I'm going to leave it to you to check. Continue. So let's think about image and kernel now. So what is the image of this linear transformation? This linear transformation going from two-dimensional space to five-dimensional space. I'm going to erase what I just wrote there. Got some stuff over here. You can do row operations to figure it out. For an arbitrary right-hand side numbers, A, B, C, D, and E. And try to figure out, are there any conditions on A, B, C, D, and E that would guarantee a solution? So the row operations are exactly the same as before, but now you've got to deal with unknown quantities in the last column. I'll leave it to you to check that you get to here as you start working on the row operations and you get leading ones here and here. We'd maybe like a leading one here and zeros below it. But actually we want to stop here. Because again, this corresponds to a certain system of equations. M plus B equals A, B equals 2A minus B, 0 equals this, 0 equals that, 0 equals this. If any of these three numbers are non-zero, the system is inconsistent. There's no solution. So in order for there to be a solution, these must all equal 0. And if they were 0, I could continue solving for M and B. But I don't care about solving for M and B here. I'm just after conditions on A, B, C, D, and E that guarantee that there is a solution. That happens when all three of these are 0. In order for this to correspond to a consistent system with the solution, all three of those equations must be true. They must be equal to 0 in particular. And the image can be described that way in set builder notation. And here I'm thinking of the image as being a set of points in R5. I could think of them as a set of vectors. But it was nicer to write it as a point. Set of five-dimensional points satisfying these three linear equations in 5 unknowns. Hey, this is a system with fewer equations than unknowns. The original system had 5 equations and 2 unknowns, more equations than unknowns. This system has more unknowns than equations. 5 unknowns, A, B, C, D, and E, and 3 equations. I could try to solve this system to try to describe the image perhaps in a simpler way. Row operations can be done here to describe the image in parametric vector form. This represents A minus 2B plus C plus 0D plus 0E equals 0. This is an augmented matrix. 2A minus 3B plus D equals 0. And 3A minus 4B plus E equals 0. By the way, E is not the number E, not the number E here. If we do row operations here, the reduced row echelon form is the final red matrix there. Each row has a leading one, a first one. You can also get rows of zeros, like we did in the previous slide. And for each leading one, each of these pivots they're called, it's all zeros below and above them. And for each leading one in a row with a row above it, or more than one row above it, the leading ones in the rows that are above it are to the left of it. Now there's no row above the first row, so you don't have to worry about that. Row 2, there's the leading one there. The leading one in the row above it is to the left of it. Row 3, the leading one is right there, first one in the row, with all zeros coming first, by the way. The leading ones in the rows above it are to the left of it. Due to the fact that these are non-zero, does that matter? No, it doesn't. And in fact, that will typically happen when you have more unknowns than equations. D and E, when I write the solution set in parametric vector form, are going to be what are called free variables. A, B, and C are going to be what are called basic variables. We'll write A, B, and C in terms of D and E. Essentially, A will be imagine adding 4d to both sides and subtracting 3e from both sides. A will be 4d minus 3e. B will be 3d minus 2e. Again, I gotta put it on the other side of the equation. And C will be 2d minus e, if I put it on the other side of the equation. And that's the answer there. Hopefully I did not make a mistake. Yeah, this is the parametric vector form. This is your A, this is your B, this is your C. Writing in terms of just D and E. We can write as a linear combination of two vectors as well. Such a linear combination, a set of linear combinations has a name. It's called the span of the two vectors. By definition, the span of these two vectors is the set of all linear combinations of them. That's a very important thing to remember. Since D and E vary independently of each other, it should make sense that, and if you also think about the parallelogram rule somehow in five-dimensional space, it should make sense that this is going to describe some two-dimensional plane. In fact, through the origin. Because if D and E are both 0, then it's going to be the 0 vector. Some two-dimensional plane in five-dimensional space. A two-dimensional plane, this is a D here, 2D, in five-dimensional space. What about the kernel? More row operations. With what? With the original capital A matrix. The augmented matrix now is taller and skinnier. Notice I now have a bunch of zeros to the right of the dashed line, because the kernel is everything gets mapped to the 0 vector. Here's what happens if you do the row operations. Oops, there's actually one more here. I forgot. Here is the reduced row echelon form of this augmented matrix. Thinking in terms of M and B, this is saying M equals 0, B equals 0. Done. The only solution of this system, called a homogeneous system when the right-hand side numbers are all zeros, is M and B are both 0. The kernel is just the 0 vector. So the kernel is 0-dimensional. The image is 2-dimensional, the kernel is 0-dimensional. Will that always happen for linear transformations from R2 to R5? Not always, but usually. And it turns out that this is enough to say that T is 1-to-1. This is enough to say that T is 1-to-1. When the kernel of a linear transformation is just the 0 vector, that actually is enough to guarantee that the linear transformation is 1-to-1. It maps distinct inputs to distinct outputs. What about the least squares solution? My students don't need to know this at the moment, but possibly near the end of the semester. Turns out that this vector, M0B0, is negative 0.95.1. We've seen those numbers before. The slope and the intercept of the least squares line that fit the data as well as possible, according to Mathematica, is what is called the least squares solution, and it has the property that the image of this point under T is the closest vector in the entire image of T to the right-hand side vector, C, for the original system. If we tried to visualize this, if this drawing were somehow five-dimensional space, which we can only imagine by analogy, we can't literally draw or imagine, the image is going to be some plane to the origin. There's the image of T. The C vector is some vector and its corresponding point that C, that's not in the image of T. But T of x0 will be a point in the image, a vector in the image, that is closest to C. This might be T of x0 right there. And it is the point in the image that's closest to T. If you draw this kind of picture, maybe this is a right angle. Maybe that's how we should think of it. Hey, we talked about angles in higher dimensions. Maybe this is, in a sense, kind of an application of that. To make this arrow and its corresponding point the closest point in the image to this point right there that's not in the image. It minimizes, least squares, a norm, and that norm is going to involve a square root, but also a sum of squares. That's why it's called least squares, as x varies over R2. There is what T of x0 is right here. It's this vector. You can check that. And this minimized norm ends up equaling this. When you take this vector, T of x0, minus C, this vector, take the norm, meaning take the square root of the sum of the squares of this vector here, of its components. You should double check that this is what you get, which is about 1.04881. That would represent this distance here of the dashed line. 1.04881. Somehow in 5-dimensional space, which you can't literally visualize. Okay? Lecture 10A and 10B were both pretty difficult, I think. But I hope you got a lot of it out of it. Anyway, make sure you do some examples on your own. Thanks for watching.